Okay, let's take a look at this problem here. We're getting into Jacobians and transformations of integrals, and this problem is just asking for the calculation of the Jacobian, which is given right here in this formula. And you see you have x in terms of u and v, and you have y in terms of u and v. So this is real easy. So you take the partial of x respect to u, that'll be -3. The partial of y respect to v would be -5, minus partial y respect to u is 4, and then the partial of x respect to v would be -4. So you have 15 minus a minus 16, which will give you 31. Now keep in mind the Jacobian can be positive, negative, whatever, but when you use it in a double integral, you have to take the absolute value of it, and then you'll be using a positive. But this number itself, before you take the absolute value, can have either sign. Doesn't make any difference. Okay. So I guess, let's see. So there were a couple of negative answers there, so those answers were possible. All right, let's see what we got here. We've got u in terms of x and y, and v in terms of x and y, which means we're going to need to get x and y in terms of u and v by doing a little bit of algebra. Now, did I even graph this one? I might not have, but you didn't have to. I know in my examples in the notes, I kind of showed the graph of what the region looked like before and what it looked like after. You know, we're essentially turning this parallelogram into a rectangle, which means our limits of integration will be constant on the inside and the outside. So you look at this, and this is basically saying that, see, if you move this over, you don't have to really graph these. That's going to be x plus y. That's going to be x plus y. And you see that we already know that u is x plus y. So you have x plus y equals 1, which is u equals 1. X plus y equals 4, which means u will be 4. Same thing here. You move this over, you get -2x plus y, which we know is v, and therefore v is going to go from 2 to 5. All right. So we didn't have to graph this, but now we have to do the algebra to get it in terms of u and v so we can do the Jacobian. And just kind of use a system of equations, elimination. You can choose whichever one you want to solve for first, x or y. I chose this one to solve for y. I multiplied the bottom one by -1, and that's going to get rid of the y's when I add. So it's going to give me an x plus 2x, which is 3x, and gives me u minus v. Therefore, x would be 1/3 u minus 1/3 v. So I use the same equations again, and this time I'm trying to get rid of the x's. So I'll multiply everything by 2, and add, and that'll remove the x's. That'll give me a 2y plus y, which is 3y, and then a 2u plus v right there. Solve for y, you get 2/3 u plus 1/3 v equals y. Now we do the Jacobian, and we can come back up here and show you the formula for that. I'll copy it down here myself. Okay. Just put it right here, and let's see. Move it over here where I can see it. There we go. So once again, I've already wrapped the absolute value, so we're trying to find the absolute value of the Jacobian. So the inside part is the actual Jacobian. It turns out to be positive anyway, but so let's see what we have here. So we're going to take the partial of x with respect to u. So it's going to be 1/3. The partial of y with respect to v right here will be 1/3 minus y with respect to u will be 2/3. And then x respect to v will be -1/3. Don't forget the minus. So you essentially end up with 1/9 plus 2/9, because you have negative and a negative, is 3/9. The absolute value is still positive, of course, and that reduces to 1/3. So the absolute value of my Jacobian is 1/3. Now let's see what we're trying to integrate here. Now you see this -4 right here. I brought that to the outside along with the Jacobian. Now, I'm not sure why I wrote it this way. It's not wrong or anything, but I guess so I could bring out that extra 1/3. Here, see, I distributed the 1/3 here, but this is because we're integrating x, and x is this right here. So I have the 1/3 back as if it just would have left it in a sort of a factored form instead of distributing it. I think I did the distributing just for the simplicity of the partial derivatives. So then I bring out this 1/3 out there to join the 1/3 from the Jacobian and the -4, and that gives me -4/9 right here. So that's just going to sit there, and we can work with what's left on the inside. So we're integrating u minus v at this point with respect to u. That's going to give me a u squared over 2 minus a uv. And we're plugging in, the one, we already found the limits of integration up here in red. Oh, went too far. See, 1 to 4 for u, 2 to 5 for v. So we plug these in for u, so you're going to get 4 squared over 2, which is 8, minus 4v for the first one. Put in 1, we're going to get 1/2 minus 1v. So it's 1/2 minus v, all followed by the negative. So if you combine the like terms, 8 minus a 1/2 is 15 over 5. -4v minus a minus v would be -4v plus v, which would just be -3v. And now we integrate this with respect to v, and we've got it. So the antiderivative of 15 over 2 will be 15 over 2v, and 3v will be 3v squared over 2. Plug in 5, and you get 75 over 2 minus 75 over 2, so that happens to cancel out. Plug in 2, we'll end up getting, right here, we'll get 15, and you'll get 6 right here. 3 times 12 divided by, 3 times 4 divided by 2 will give you 6. So -4 over 9 times -9, basically, just turns out to be exactly 4. Just double check there, and there it is, answer A, 4. Very good. Let's take a look at the next one. Looks like it's the same. That's weird. That's okay, but same u and v, isn't it? Yeah. Well, the next one will be a different one. U is going to go from 1 to 4, v is going to go from 2 to 5, and now we're integrating a different function, though. So those will be our limits of integration, and now we do the process again where we solve for x and y in terms of u's and v's. So once again, I just chose to solve for x first. Didn't have to. But I multiplied the bottom one by -1. Oh, I guess this is going to work out exactly like the last problem, isn't it? Yeah, it's the same u and v, isn't it? All right, well, okay. So I'll kind of speed up through this a little bit. So this is exactly going to be the same as the last problem. I guess I didn't realize that when I picked these. Or didn't pay too much attention. So, yeah, all right. So it's exactly what I explained right back up here. So I'll save the time then of explaining that. Same Jacobian. Well, at least we'll get a new problem for the next one at least anyway. Well, the integral is going to be different here, but same Jacobian, 1/3, just like the last one, and for the same reason. Not a coincidence, same numbers, same everything. So I pull it off to 1/3. There's v going from 2 to 5, u going from 1 to 4, and we're integrating 2x. And here's what x is. 1/3 u minus 1/3 v. So there it is. That becomes 2/3 u minus 2/3 v. There's the 2x. And here's v right here plus 5y. Y plus 5y will give me 10/3 u plus 5/3 v, and then du dv. So naturally I want to combine like terms before I integrate. Makes it a little easier. So a 2/3 u plus a 10/3 u would be 12/3 u, which will be 4u. And minus 2/3 v plus 5/3 v is 3/3v, and that's just v. So now that condenses down into 4u plus v. So with respect to u, that antiderivative will be 2u squared, and v will be uv, going from 1 to 4. So I put in 4 right here, I'll get 2 times 16, which is 32. Put in 4 here, I'll get 4v. Put in 1 for this one, 2 times u squared will be 2. Put in 1 for u, you'll get plus v. So then we can combine these together. I get 32 minus 2 is 30. 4v minus v is 3v. And with the 1/3 coming out there, you didn't have to do catch what I did here. It'll still work if you didn't do it. But I just happened to notice that 3 goes into both of those terms. It's very important that it goes into both of them to do what I did. So essentially then I just knocked out the 1/3 and that becomes 10 minus v. But that's not important. You can just forget that and just integrate 30 minus 3v. That would be okay. I guess I just saw that and felt like the need to do it. So the antiderivative 10 would be 10v, and then the antiderivative of v itself will be 1/2 v squared. Put in 5, put in 2, we'll get 50. Of course, you can use your calculator to do all this, obviously. You don't have to do it like this, but 25 over 2. And then put in 2, I'll get 20 here. 1/2 times 2 squared will be 2. And that all condenses down into 81 over 2, which was answer A. Let's take a look at the next Jacobian. Okay, something different finally. So now you can see the common thread here, and it's kind of telling you what u and v are right here anyway. But if you move that over, you get negative 2x plus y, so that's going to tell you that u is 6. Same thing here, so you get u equals 7. And then here, this is 9x plus y right there when you move it over. So it makes that equal to v. V equals 5 right here, and then v equals 6. So u will go from 6 to 7, and v will go to 5, from 5 to 6. And you can kind of see right here that the function we're going to be integrating, of course, don't let that trick you that negative 2x plus y is the same thing as y minus 2x. So we're just going to be integrating u times v. That'll be the only thing integrating, but we've got to get the Jacobian that goes in there with it. So same thing, I'm eliminating here. I'm choosing to eliminate the y's first. And that gives me a negative u equals 2x minus y. Add together, I'm going to get negative u plus v. I'm going to get 11x. Of course, the y's cancel. That was the plan. And then you divide both sides by 11. Here, I sort of did because it didn't really, I could have used a fraction, I guess, but I decided not to do it that way. I multiplied the top one by 9 and the bottom one by 2, and that's going to give me a negative 18x and a positive 18x, and then they will cancel when I add. So that's going to give me a 9u and then a 2v on the left side. X is canceled, of course, and that's going to give me 11y when I add 9y and 2y. And then, of course, then divide by 11, and you have this. So let's take a look at the Jacobian. And we're going to have the partial of, let's see if that's still snipped in here. No. Can bring this back down again. Haven't tried to commit that to memory yet. It's not too difficult, obviously, but I haven't done it, so don't want to mess it up. because of not... Oh, it's already... I'm talking about... Oh, it's already right there. Excuse me. Here it is. I don't know what I was thinking about there. So, partial x respect to u would be negative 1 over 11. Partial of y respect to v will be positive 2 over 11. And then partial of y respect to u will be 9 over 11. And then partial of x respect to v will be 1 over 11. So essentially we have negative 2 over 121 minus 9 over 121, which is negative 11 over 121. Now that the Jacobian, that reduces to negative 1 over 11. So technically the Jacobian itself is negative 1 over 11, but we have to take the absolute value of that to put it into the integral. So that's why we have positive 1 over 11 here, but the inside does equal to negative 1 over 11. Just want to make that clear. So I immediately put the Jacobian on the outside. So we're going 6 to 7 on u, 5 to 6 on v. Antiderivative of u du will be 1/2 u squared. So I went and just took the 1/2 all the way to the outside. Plug in 7, plug in 6. And you square those. 49 minus 36 will be 13. So that'll be 13v. The antiderivative of v will be 1/2 v squared. So the 13 is still there. Now I have the 1 over 22. The 1 over 2 we just got from the antiderivative and the 13. Now I have v squared here. So I've got 13 over 44 from the constants here multiplied together. And then the v squared will give me 36 minus 25, which is 11. And I just went ahead and reduced it. Looks like, well, I didn't reduce it until after here, but if I would have reduced it first, 11 over 44, either way, you'll end up with 13 over 4, which I do believe was one of the answers. Yes, it was answer C. So yeah, whether you reduce it like I did the first or wait till after you get to the final number, either way is fine.